Okay, so the next comment that I want to make, and it has to do with a problem that I'm going to put up in a minute, which you can't really respond to yet because I haven't kind of alerted you to the point. But it has to do with the following. If I have a signal, or if I have a system, or I have a system function that's minimum phase, then it has a very interesting and very important property. It has lots of other important properties, but others that we'll talk about. But the one I want to talk about is the fact that if I gave you the magnitude of the frequency response, and I didn't tell you what the phase was, but I told you that it's a minimum phase system, that's sufficient information to uniquely determine what the system function is, or what the impulse response is, or what the phase is, knowing just the magnitude. Now, it's a very, very interesting, fairly deep idea with a lot of formality to it if you become formal about it. And actually, a little bit of history here has to do with going back to the early days of circuit theory, when the issue was designing passive RLC filters. And if, for example, you're building you want to design a low-pass filter, and you'd like it to have certain group delay characteristics or phase characteristics, what you'd like to be able to do is design it where you can independently specify the frequency response magnitude and the frequency response phase. And people tried to do that for the driving point impedance, for example, of an RLC circuit, a passive RLC circuit. And at one point, it was actually Norbert Wiener that pointed out to Gilliman, you can't do that. The reason you can't do it is because the driving point impedance of a passive system has to be minimum phase. Why does it have to be minimum phase? Well, the driving point impedance is reciprocal as the driving point admittance, and either of those has to be causal and stable if the circuit is passive, obviously, causal circuit. And in other words, it has to be causally invertible. And so it has to be minimum phase. And the deeper math for that is what's referred to as the Hilbert transform. We're not going to be going into the Hilbert transform, but it's important to understand that there is some serious math related to how, for a minimum phase system, you would construct the phase from the magnitude, or for that matter, the magnitude from the phase. So I'm not going to get into that formality, but I want to basically use a poor man's proof, which is kind of a mixture of intuition and what I call proof by intimidation, where I sort of put some things up and I stare at you directly and say, how could it be otherwise? But think about it. Suppose that I gave you h of e to the j omega squared. Well, what that is h of z times h of 1 over z, with z evaluated at e to the j omega. So you can think of it as analytic continuation, where I see an e to the j omega, if this was a rational expression, where I see an e to the j omega, I just replace it by a z. What I'm doing is I'm analytically continuing into the complex plane from the unit circle. So I can intuit sort of what h of z times h of 1 over z is. Now, if I look at h of z times h of 1 over z, and let's say I have a pole at z equals z sub p k, p meaning pole, k meaning there can be more than one of these, then in h of z, then I'm also in h of z times h of 1 over z, I'm going to have a pole someplace else. I'm going to have a pole at the reciprocal location. So I'm going to have a pole at z equals 1 over z sub p k. And the same thing is going to be true for zeros. So in h of z times h of 1 over z, wherever h of z has a pole, this expression is going to have a pole at the reciprocal location. And the same with zeros. Now, if I tell you that the system is minimum phase, can I, if I give you h of z times h of 1 over z, can I figure out which pole is at z sub pk and which is at the reciprocal? Well, the answer is yes, because if the system is minimum phase, I mean, I look at all these pairs and I say, well, if it's minimum phase, all the poles and zeros have to be in the units, inside the unit circle, so I immediately know how to factor this out. So that's the basic idea. And that's the basic intuitive idea for why, if I give you a minimum phase system and I give you the magnitude of the frequency response, the phase is uniquely specified, which is really pretty interesting. I encourage you to just kind of get this under your belt because we're going to be wanting to refer to this as we move forward and talk about some issues of quantization and when we're talking about random processes. If I have a system excited with a random process with the power spectral density given by that, the power spectral density of the output is the power spectral density of the input times the magnitude squared of the system frequency response. And so this just relates back to exactly the point that I'm raising here, which is if you don't know whether or not the system is minimum phase, you don't know how to sort out when you're kind of looking at this and inferring what h of z times h of 1 over z is, you don't know how to sort out, well, you know what to do with the poles. Because if I'm telling you that the system is causal and stable, you know that the poles for that system will be the ones inside the unit circle. But you don't know how to sort out the zeros. So it's always a question of where the zeros are. However, if I tell you that the system is minimum phase, then you can, for example, uniquely get the impulse response of the system or the frequency response of the system by exciting it, for example, with white noise. And you can infer from the power spectral density of the output what the frequency response is in terms of both magnitude and phase. Now, if I told you that I don't know whether it's minimum phase or not, and I'm exciting with a random process, let's say white noise, can I still, by doing something with the output and the input, reconstruct both the frequency response magnitude and the frequency response phase? Well, the answer is yes, but in that case, what I need to do is look at the cross power spectral density between the output and the input. And that will capture the phase.